Hello, my name is Gabriel Han, and I'm going to be giving a quick walkthrough of a poster that I made on Cellular Automata. So what it is, it's a charge-based computing paradigm, and it allows faster computing speeds with less power dissipation and in smaller devices. So a quick walkthrough of how QCA works is you have this cell with multiple quantum dots within it, and interactions between neighboring cells enable a general purpose computing. If you want a more in-depth explanation and visualization of how that works, I put a link in the description that gives a nice visualization of all that. But pretty much after you have that process, you can add more dots to the system. And what you can do with that is you can create active and null domains. So initially, in this cell, you would have all the electrons, which are these red dots, unactivated, and they would be in this bottom row. And then you can have an active domain, which would throw these electrons up, and then you can go back to that general purpose computing because they're all activated, or you can deactivate them and bring the cells down. So that's very important because what we can do with that is we can create clocking fields, which this model down here represents. The white is the clocking field, and all these little squares are cells that are all in a line, affecting each other. So they're all in the off state when they're in this black area, and this white clocking field activates them. And with that, you can create gates, or usable gates, and that means that we can do higher level computing. So what I've been working on is addressing the power dissipation within QCA, because with using molecules as the basis for computing, whenever you're changing states to ones or zeros by switching where the electron is, the whole molecule starts vibrating into what we call a vibron. And that's what causes the power dissipation, is those vibrations. When you have so many of them, it releases a lot of heat. So the way that those vibrons are put back into a ground state, which is necessary for computing, they need to not be shaking, is that QCA uses environmental coupling to put them into that ground state, and so that it can get more accurate and usable calculations. Because if there's too much power dissipation, there's too much heat, and then the whole system is just going to melt. So to model the effects of environmental coupling on the system, we used a 3-dot cell system with the molecule called Zwitter ionic nidocarborane. We chose this molecule because it has properties necessary for modeling the electron-vibron coupling, as well as the vibronic motion that is causing the power dissipation. So over here, you can see a general model of how the physical system is working. So you have the electron, and then it changes into the vibron when it starts shaking, and you have, in red, you can see the power from the clock, which is external power, and the power from the driver, which is setting it into 1 or 0 sorts of states. And then you have the power that is released to the environment. So all of that is modeled by this general power equation. To simulate the electron-vibron interactions, we use an equation called the Lindblad equation, which is a complicated and time-consuming equation to calculate because it contains a lot of very large matrices. So in order to calculate realistic simulations that have even larger matrices, because we use this Hamiltonian, which describes like the whole environmental system as well, we had to use high performance computing, because otherwise these calculations would have taken ridiculously long. So, after running these calculations on the Baylor supercomputer for a couple months, we've gotten most of our results back, and they're looking pretty good. They're showing us that higher power dissipation values are resulting in, or no, sorry, higher environmental coupling values are resulting in lower power dissipation, and it's a consistent trend. So, as you can see at, I'll zoom in a little bit, with environmental coupling values at 22 tau vibron over T1, which is just the environmental coupling, the power dissipation is lowest. However, none of these values quite on their own reach manageable power dissipation, which is at this x-axis, which is 100 watts per centimeter squared. That's where we need to get to have manageable power dissipation. So on its own, changing environmental coupling doesn't get us there. But when we combine these ideal higher parameters with other parameters that we've tested, we can create a molecule that has the perfect parameters for reaching manageable power dissipation. But overall, this method and this model were very effective in determining the correct environmental coupling powers to reduce power, and the best values occurred at 22 T vibron over T1. This is, like I said, still too high, but we'll work with chemists who can test the actual molecules in a physical environment and provide data that can assist us in finding ideal configurations, or maybe they'll just tell us that we need a different molecule, and then we can keep going through this cycle of creating, testing, sending back data back and forth until we find the ideal configuration. I would like to thank Dr. Eric Blair, who is the one behind all this at Baylor University, and I'd also like to thank Baylor University for the grant and providing the opportunity for me to do this. Anyways, I hope you enjoyed the video. If you have any questions, you can leave it in the comment. I'll also have a link to Dr. Blair's YouTube channel where he goes much more in depth into how all of this works and how it can be used. And I would really recommend, if you're interested, going to his channel and just looking at what he has to offer. If you'd like to contact me personally, my email is right here in blue. And I hope you enjoyed the video. I hope you have a great day as well. Thank you.